If this is a lesson on conditional probability, then there has to be a formula. So let's talk about that. Let's get into this. Now you can derive a formula for the conditional probability of two events, the scenario P of B given A. Probability of B given A. So let's let A be identified. And it's probably a good idea somewhere on your notes when you're working these things out to actually list it. A is rolling a 5 first, and then B should represent rolling a number less than or equal to 4 on the second. And then they've done the work for us. Thank you so much for highlighting our outcomes and which ones are arranged there. If the probability of A, which again, this notation was catching me off guard too, so I want to make sure you're not caught off guard. It means rolling a 5 first. Well, how many situations from our table are rolling a 5 first? And it's these ones. There are 6 of them. But it's out of the entire table. So separately, by themselves, the probability of A is considered out of all 36 outcomes. 36, 6 out of 36, which is, of course, reduces down to 1/6. Shouldn't be a surprise, though, that if there are 6 sides on the die, getting a 5 is one of those 6 sides. But when you have 36 total outcomes, 6 out of 36 of them are, that happened. First try. How about probability of B, rolling a 4 or less second? So 4 or less are these outcomes. There are 24 of them. And again, a standalone probability of B is taken out of the entire sample space. So in this sample space, there are 36 total numbers. That leaves us with a probability of 24 out of 36, which reduces to 4/6. So if we want to talk A and B, this use of the word and is different from the given line, that given bar in the conditional probability. A and B is where there's overlap. And so how many of these cells are, box in the table, how many of these cells are in the overlap of 4s and the 5? 4 of them. And not a condition. And is like a conglomerate. It's all of it still put together, and we're looking for what intersects between the two different categories. The total is still out of 36 total outcomes, which means our probability of getting a 5 first and something like a 4 or less second is going to be 4 out of 36, which reduces to 1/9. Here's the part that's the formula. In the scenario of B given A, so the probability of rolling a 4 or less second, given we rolled a 5 first. The two things that happened there is that the total outcomes, this 6 is the number of total outcomes. So I'm going to highlight there as well to let you know. I'm kind of working this table a little bit backwards. The 4 out of 6, 4 of them are in this category. So it's like the intersection. And then the bottom is 6 total numbers. Our probability is 4 out of 6, which reduces to 2/3. This also reduced to 2/3. I just didn't call it out until now. So there's some dual equivalent probabilities in our table. It doesn't always happen, but there's a reason why it happens right now, and we're going to study from that one. But pay attention, the key thing is the highlight. This desired outcomes for probability of A happens to be the total outcomes for the probability of B given A. There's a connection there on purpose. Use the table to verify that event A and event B are independent. Well, if we look at the probability of B given A, that's 2/3. And then we look at the probability of just B, that's also 2/3. So because those two probability scenarios are equal, probability of rolling a 4 or less on the second roll, probability of rolling a 4 or less on the second roll given you rolled a 5 on the first roll, they're equal. Makes them independent. And that also kind of like we've seen that before. If you roll a 5 first, like who cares that you rolled a 5 on the first roll? If the next time the die is rolled and it's 4 or less, that did not get any influence physically from the 5 that rolled before it. So which quantity in the table is equivalent to the other? Highlight time. This one to this one, which we just saw. The probability of, where we at? Which quantity in the table is equivalent to the number? Oh, I highlighted too soon. Got a little highlight happy. The number of desired outcomes. So look right here how the desired outcomes are the same. So it's the number of desired outcomes for probability of B given A is equivalent to the number of outcomes for the probability of A and B. That's part of the formula. I hope you were awake for all of this so far. Rewatch the video if you didn't. The fact that these are the same number is intentional. It is part of the conditional probability. Flip down to the next one. Which quantity in the table is equivalent to the total outcomes of B given A? And so I've got one more highlight color. You can use highlight colors if you want to, but it's your call. I want to make sure I got this one clear. Yes. So the probability of B given A, which quantity in the table is equivalent to the total number of outcomes? So this is what I highlighted on purpose. I knew this question was coming. The 6, the total outcomes for probability of B given A is the number of desired outcomes. I need to change this one to desired for probability of A. Those two equivalencies, the 4 is here and the 6 is here, are gonna pop up in the formula for conditional probability. So stick around, we're gonna keep building this. Page 851 is next. There is a way for us to formula approach the way to calculate conditional probability. I still think in any case, with the questions you're gonna be seeing in this class at this level, if you're lost, draw everything out, the entire sample space of all possible total outcomes, and start looking at what your desired outcomes are. Some questions before you leave. What method do you currently use to determine conditional probability? This is my favorite method, certainly for right now, certainly before we talk about a formula. Thanks for watching, commenting, liking, and subscribing. I'll see you on the next episode.